So we'll now look at an example making use of variance inflation factors in multicollinearity. The example is a data set from California, the California Standardized Testing and Reporting, or STAR for short. And there are variables about school performance, test performance, and demographic backgrounds. There were 420 schools here. So the unit of observation is the school. This is dating back to 1998 and 1999. So when we talk about having computers, remember this refers to 1998 and 1999. I got my first laptop when I started working in 1999. So test scores are the average of the reading and math scores on a standardized test administered to fifth grade students. So this is fifth grade here. Right. So the average of reading and math, and I guess we did that so to just have one y variable as opposed to several ones, reading and math. Here's an overview about the variables. Average income, I'm starting from the bottom. Average income refers to how rich the district is. And so, maybe richer districts are more successful. Meal percentage and CalWORKs percentage is a sort of a marker for lower socioeconomic studies or families in need. The same is the percent of English learners. So this is California. There's lots of Hispanics, yeah, especially in the middle part of the I was going to say province of the state, and the student-teacher ratio and the number of computers is here somewhere, and number of teachers and so forth, enrollment total. Okay. So now I'm running merrily my regression. And what do I see in terms of R squared? 88.7, 80%. That's a very good R squared. We are very happy. So this model really does explain the test scores, the average math reading scores, quite well. This is quite good. So what do we have in terms of significant variables? Constant, we ignore. Average income. So that's significant. So this looks like if the district is richer, the test scores also tend to be higher. Okay. And then we have here two significant variables, meal percentage and English learners percentage. So so the students that qualify, if you have a lot of students that qualify for meals, so lower socioeconomic status, then you tend to have worse test scores. So in terms of income here, that sort of corresponds to the average income better, and lower income, so you need meals worse. English learners clearly are going to have a harder time with the reading. So also lower test scores. And here, expenses per students, just barely significant here. Barely. Okay. All right. So let's run the variance inflation factors, see what happens. There. Here we have a stunning surprise. We see some really, 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 really large values, 265. Even if you don't know what's large, relative to those numbers, that's large. What is large? Well, what is large? Oh, here's the corresponding code in R. There is a separate VIF command in R. What is large? Montgomery and Peck, the authors of a prominent book on linear regression, say, practical experience indicates that if any of the VIF exceeds 5 or 10, it is an indication that the associated regression coefficients are poorly estimated because of multicollinearity. And Abraham et al. Suggest VIFs exceeding 10 may indicate multicollinearity. This is good guidance. In practice, we do what we can. We certainly are worried if there's something above 10 or wanna look, but we do as good as we can. And sometimes large VIFs are unavoidable, but we're trying our best, right? So let's look at the two variables that were indicated here on the VIF, and that was enrollment total and teachers. They had the largest ones, roughly the same size. And if you look at that, it looks like they're highly correlated. And then if you think about that, it's sometimes good to think about these things. Well, guess what? If you have more teachers, you're going to have a higher number of students enrolled because you hire students because you get more students. You hire teachers when you have more students. So this is not surprising. They're both really a measure of size of the school. Okay, and in this data set, we have 20.3 students in a class on average. So it's no surprise that here, roughly speaking, the enrollment total of a school can be calculated as 20.3 times the teachers, approximately. So we want to remove one. Let's see which one was higher. Teachers was a little higher. Maybe we remove teachers. Okay, we might do something else if it makes sense to us because we want to interpret the model, but may as well take teachers here. Okay, we've done that now. Has something changed? 80.87. Isn't that exactly the same as we had before? Or if it's not exactly the same, it's almost exactly the same. So teachers really contributed nothing to the R squared beyond what we already had. But when you add a variable, the R squared necessarily increases, right? Or stays the same, but increases. And if you remove one, the R squared necessarily goes down, but in this case, I guess went down by almost nothing. So let's look at this. So number of computers, totally irrelevant. Enrollment total, it's still not significant, but, and I think the rest is the same. I'll get back to enrollment total in a second. Average income, same effect. Meal percentage, secondary learners, same. Here moved around from 5% to 4.7, big deal. So similar interpretation. The enrollment total is also not much different, but the standard error has changed dramatically. And so here we have 3 zeros and then 2 9. And before we had, I'm gonna go back some slides, bear with me. Here we had 2 zeros and then 1 6. So it's 2 9 versus 163, 29, 163. That's more than 5-fold increase. So if you put the enrollment total back in, the standard error increases by a factor of more than 5. And yeah, I guess we could have known that from the variance inflation factor directly. And the standard error, of course, is directly related to the width of the confidence interval because it's just a multiple of that, right? Okay, so we're going to claim success. Nothing much has changed in the interpretation, but we have reduced the standard error. That's what I'm saying here. Let's look at VIF again. And it's much better, right? Before we had 250 and almost had a heart attack. Well, I did. And here we are much better. We have values of 8 and 7. This is not outrageous, but given that we are looking at it, let's look a little more. We have enrollment total and computer are 8 and 7. Let's plot and see what happens. This is clearly correlated. And it's actually shocking how correlated it is. It doesn't look that correlated, but when you look at the values, it's 0.93. So I would not have guessed it's so high based on this. So here's a question for you. If we know that the correlation is 0.93 between those two variables, and you regress just on this one variable, so number of computers is a function of enrollment total, what is the R squared of this regression? Or do we know it? I will leave you to answer this question, and I am moving on to the next slide. So we were talking about computers and enrollment totals. And if you have more students, you probably will tend to have more computers also because, well, it's a bigger school. So, but rather than having both variables be a measure of size of the school in a sense, because in a vague sense, the number of computers is also a measure of size. It might be more informative if we create a new variable and say computer per student is the number of computers divided by the enrollment total. So rather than having the absolute number of computers, we compute the number of computers per student. Okay, let's look at correlation. Before we had a correlation of 0.92. We're adding this new variable, and the correlation to enrollment total is negative 0.21. So much reduced relative to 0.92. And to the other one, it's almost non-existent. So if we remove computer, the correlation, which was 0.92, is gonna go away and gonna be replaced with what? 0.21. Beautiful, absolutely beautiful. Let's run the regression. Here we have the revised regression. R squared, 0.8093. I think before we had 98 or something. Almost identical. We didn't lose anything. Well, we have a transform variable, right? So it's not so clear what that happens. But so I think it's very similar. I don't remember the exact other value. So let's see what happens down here. This is still the same coefficients, still significant. For this variable, expenses per student, significance dropped to 8%. And enrollment total is still not significant, but it has a good standard error. And the computer per student now is marginally significant. So 8.7%. So it's not significant if we insist on alpha equals 5%, but it's gotten a little more there. But it was good to do that. So let's look at the revised variance inflation factors. Now we see we dropped completely. The 8 is gone, the 7 is gone. We still have the 5.7. And before, enrollment total is down to 1.3. It's at the bottom of the list, except for our new variable, which is even lower. So we did a really exciting, good job here. All right. And I think this is it. This is the end of this segment.